Welcome to my week 5 problem number 3 video explainer. So in this problem we are given an oscillator with a mass m and a spring constant k, and we are also given that the driving frequency is equal to the same thing, I guess, as the undampened frequency, which is going to be equal to the square root of the spring constant over the mass. And we are also given an external force, which is equal to F0 sine the driving frequency times time. And we're also told that the oscillator is subject to a damping force. And we can find that damping force through negative b times the velocity with respect to time, so v of t. So we are told to find the steady state amplitude in terms of m, k, b, or f0, and we are also told to explain why the undampened angular frequency is also equal to the driving frequency in the solution, and then we are supposed to take the derivatives of the acceleration and velocity with respect to x. And yeah, so there were a lot of tricky parts in this problem, and I will go through those and explain my reasoning to the best of my ability. So, as mentioned earlier, there is an external force acting on this particle, in this case the oscillator, and that is given through F0 sine that driving frequency times the time. And there is also a damping force, and as noted, or I try to note in this diagram here, that in this case with this resisting force, that this amplitude ends up decaying exponentially in a position versus time graph, with a being the initial amplitude and negative a just showing the two amplitudes, as I said earlier. But yeah, just the main thing to note is that it's decaying exponentially, and it is decaying at a rate with respect to e, so an exponential function basically. So given that we were given the damping force and what the external force would end up being, I found that the force ma plus bv, which is the force from the dissipation, plus kx from Hooke's law, aka the restoring force, that's going to be equal to the external force. So the sum of the ma plus the dissipation at an angular frequency, which is equal to the spring constant over m, we were supposed to find the significance of that, and I was having a little bit of trouble with it, but I figured that it has something to do with relating the connection between the dissipation force and the restoring force. And in regards to finding the acceleration with respect to x, or the position, I found it obviously not hard to integrate with respect to time, as we were given a couple of useful values. So here I integrated the acceleration and the velocity and the position with respect to time. However, we were supposed to do it with respect to x, so I was having a little bit of trouble doing that. Additionally, I was having some trouble differentiating between just the amplitude and the steady state amplitude. And yeah, so that was kind of one of the tricky parts. And I figured that my thinking, at least, was that through finding the damping position, which I told you was an exponential decay problem, which would be the amplitude times that e, and then raised to the negative bt over 2m power, I figured that would be somewhat useful. However, I was having a lot of trouble figuring out how to put it into practice. And as also this, so I guess what makes this problem somewhat easier is that, so those angular frequencies, given that we can relate the angular frequency of the undampened oscillator and substitute that for the driving frequency that kind of simplifies some things. But yeah, and then I just wrote some things that kind of tricked me out, just writing derivatives with respect to x for the acceleration and velocity, and also relating the external force to the angular frequency was something that I was just conceptually trying to do and was having a little bit of a problem with it. But yeah, and just how it relates to stuff we were doing in class. The big thing is dealing with like the idea of damping and that amplitude changing with exponential decay. So yeah, that was some of the tricky parts. I had a lot of trouble with this problem, so thank you for bearing with me. But yeah, thank you for watching.